recording locally. So this one, we're gonna, and first of all, my apologies if I'm sitting for you. Okay. So we're going to talk about pointers today. We went through IPC 144 pointers at the beginning of the semester, right? I showed you all the pointers are and all the good stuff. So today we're going to talk about pointer arithmetic, a little emphasis on what pointers are, and then we're going to talk about smart pointers and why do we need them. Again, I want to put the emphasis on the fact that all the pointers and all the features that you see in C++, most of the features that you see in C++ are simple stuff that are done by smart people to make your life easier. So they sound fancy, but when I do it, you'll see you could do this with your own knowledge. And then somebody did it and called it a smart pointer. All right? So it's not something extraordinary, like many other things. So C++ is one of those languages that is built on itself. It's using its own implementation to create new things. And that's C++ 17 and yada yada. And anyway, so just be aware of it. You have seen the questions for quiz 2, so be ready when you're coming for the next session. That's going to be the quiz. Okay? So, pardon me? General discussion on MS Teams. They're there, right? Okay. I was actually sitting in the other class while waiting for the class to get empty, and I wrote those things. All right, very simple stuff, just file thingies that I want you to do. So, any questions before we start? Hopefully, it's going to be a short session. So, we are talking about pointers. So, essentially, we said that pointers are very simple and straightforward variables. They're essentially unsigned integers whose job is to hold the address of other variables. That's all what they are. So when I create things like this, when I say character name Fardad is 50 and I put the literal value over there, or I do something like this, that name over here is essentially a pointer pointing to a chunk of memory that is within the executable that you have. That's not in heap because it's a local variable. We'll be okay with that. Okay, so we know that if I say over here name, if I say cout, what is going to get printed over here? No? What's going to get printed? Loud, please. What's going to get printed? Seriously, you're thinking? F. F is going to get printed. Target of name. Name is pointing to the beginning of Fardad, and therefore when I run this program 3 years later, 4 years later, F is going to get printed. We okay with that? All right. Now, if I say over here, what is going to get printed over here? D. All right? We're okay with this? Oh, you don't have? I'm trying. It shows that it's shared. Let me unshare it and share it again. You have to report a bug. Can you see it now? Okay, perfect. All right. So going through it one more time, name over here is pointing to a chunk of memory, 50 of them. The first 6 are pointing to FARDAD, and the rest of them are all 0, based on the definition of initialization of arrays. Then I have A10 over here, which is essentially 10 integers. The first 6 of them are set to 10 to 60, and the rest are 0. All right? When I say target of name, because name is considered to be a pointer, where name is pointing to is essentially here. When name is pointing to is essentially here. Therefore, when I say target of name, F is going to get printed. When I say target of name plus 3, it's going to add 3 to name, and therefore it's going to go 3 addresses forward. Therefore, it's going to stand right before D. When I print it, D is going to get printed. Are we all okay with this? All right. All right. Although I said name is a pointer, there is some kind of a problem in here. I'll show you what the problem is to understand exactly what pointers are. If I say over here character pointer, CPTR, and if I say integer pointer, APTR. So APTR is a pointer to an integer, and CPTR, let's call it NPTR, is a pointer to a character. And when I say this is set to name, and this one is set to A, we know that essentially I have now 2 pointers pointing to the array, right? So if I take the values over here, and I put over here NPTR, and put over here NPTR again, we'll know what's going to get printed. And I'm going to actually do the same thing for the integer and replace this with A. A and A, and when I print this, you know exactly what's going to happen. So essentially, it's F and D for the first one, and 10 and 40 for the second one, and we know exactly what pointers are. Are we good down to this point? This is the knowledge that we had from IPC and OOP. What is interesting over here is size of these pointers. If I say cout, and I'm going to say over here APTR, and I have NPTR. Now, that's the walkthrough that you're going to get for your quiz. If I put a quiz thingy for you, if I add some walkthroughs to your quiz, I'm going to tell you what is the output of lines 19 and 20. Loud, please. Oh, give me a second, by the way. Assuming that I have a 64-bit operating system over here, which means the address is a 64-bit address. Assuming that I have something like that, then, as I see you're not talking, and I have to bring the talking stick. Like that, I'm forcing you to talk. And I see people at home are quietly sitting over there. Don't say anything, so. Oh, it's off. Thank you so much. Absolutely welcome. All right. So now, my friend, what is the output if I have a 64-bit environment? What is the output of line 19?
I think.
4. You're saying 4. It might be 8, because what is the size of a pointer? It's a 64-bit operating system, right? A 4-byte, the biggest address that we have is 4. In a 60, so you see over here, I have 64 up here. So, and what about NPTR? If APTR is 4, then NPTR is 4 too, because they are both pointers. It doesn't matter what is the target, right? If I run it like this 3 years later, so you see they're both 8, right? Now, if I do it like this, and I run it, then I have 4. You follow what just happened? So depending on what type of operating system you have, what kind of environment. I can't say, because you can have a 64, mine is a 64-bit operating system. Well, when I have a 32-bit compiler, it doesn't matter. It's going to use the pointers at 4 bytes. But when I have a 64-bit operating system and a 64-bit compiler, now it's 8. If you have a 32-bit operating system, and then, so that's why I say environment. That's better. It means everything's 8-bit. Everything's 8 bytes. So, so we are cool with this. We're OK with this, right? All right. OK, so I'm going to, yeah. So now I'm going to do the exact same thing over here. And instead of putting APTR, I'm going to put the A. That is the name of the array. And in here, I'm going to put name. Now, what is the output of line 21, my friend? Pass the microphone. You answered enough. I really appreciate that. OK.
It's going to be 4 into 10.
It's going to be what?
Because
let's make this back to 64, because we are doing 64. So what's going to be the output?
not sure.
Not sure. OK. It's good that we are not sure. If we do it like this, you will see that, surprisingly, although those things are pointers, but when you look at the size of the pointer for an array, then it becomes the size of the entire array. You see that? Now I have name. Name is NPTR, right? It's 50 characters. So therefore, size of name is 50. I have A. A is 10, correct? And there are 10 integers. Therefore, the size is 40. But didn't we say that in C language, the compiler is not aware of what is the size of an array? It appears that it is, right?
It's not the exact size. It'll be how much is allocated. It's not going to be the exact size of the array, but how much is allocated.
It is the exact size. Oh, you mean exact size? You mean for that with that's data inside the array. Who cares? Data, you're counting the data until you get to the null termination. I'm not talking about that. I'm talking about the size of the array. So essentially, if I do something like this in here, and I pass those things to the array, so I'm going to say character name. And in here, I'm going to say integer A. Right? And now I'm going to say cout. I'm going to actually bring those two things over here. and print the size of the two. And now I'm going to say foo, name, and a. Right? What am I doing now? I'm passing the arrays to the function. So based on what I see over here in the function, so I'm going to say in foo in here. When I run the program, we're going to be surprised that, hey, when it's passed to an array, it doesn't know what the size is anymore. So what is the difference between the name in main that is actually a pointer and the name in foo that is the same pointer? And I use it the exact same way when I say target after this one. It's the same thing. So what the heck is going on here? So why the size of one over here is 50 and the other one is 8? This is, you can actually create a pointer and tell that this pointer is only supposed to hold the address of an array with certain size. You can enforce that. That's the enforcement that you see over here. Okay? I'm not going to go into the details of it, but because for some reason I think it's removed from the pointer part of the, we used to teach it, but I don't see it over there anymore. I'll take a look at it if we need to. I'll let you know. But so you can actually create a pointer that is just a pointer to an array and say, I want this pointer to only be pointed to a specific size. So I could create let's see if I recall it correctly. Yeah, I can't do it. Forget it. I'll explain it later. It's too rich for our blood at the moment. Let's keep it like that for now. But again, just letting you know that in a local scope, when you're creating an array, the array knows what the size is. But when you pass the address to another scope, you don't have the size anymore. That's the biggest mistake that students make. They think that when they pass an array to a function, the size goes with it. But we know that it doesn't. And that shows why you can use size off inside the local scope to know what the size is, which is useless because you just wrote it over there. You know it's 50. You don't need to, unless you have like 500 lines of code and you forgot what it was. You know what I mean? But if you pass it to another scope, then it's gone. You have to actually do the size. And that's why we have the vectors. We have all the containers because of that fact. Okay? So we wrapped the array inside another class, and we passed all the information with it. Are we okay down to this point? We'll come to that point later. I'll explain later on. Well, how do we set all those things, and what do I mean by that? So that's that. Next one, pointed arithmetic. I showed you over there what happened with adding something to a pointer. But let's kind of look at it more in detail. So let's call this one character pointer. Because I have the code over here as character pointer, I want to copy it. And this is integer pointer. Okay? So if I do like this, if I say reinterpret the value kept in the character pointer to a size t, and I do the same thing over here with the integer pointer, it's going to tell me where the, and I can do the exact same thing. So in here, I'm going to write A, and in here, I'm going to write, oh, sorry, in here, I'm going to write name, and in here, I'm going to write, what is the other one? A. Of course, I assigned it to each other. So when you run this, you'll see the addresses of the two are exactly the same, right? Right? What we need to understand is that if I say over here CP plus equal to, and I write over here IP plus equal to, when you add 1 to a pointer, the size of the target will be added to the pointer. And that's how it can actually traverse through an array. So when I actually run this program now, you will see that. Let me just put some separator over there. Just want to be able to see properly. Okay? Now, this is 32. You see that? And it becomes 34. I added 2 to a character pointer. Size of a character is 1. Therefore, 1 is added to it. Look at here. It's 12. Then it becomes 20. When I say plus equal to, it adds the size of 2 integers to it. Each integer is 4. Therefore, 8 is added to it. Is that clear? You understand? All right, perfect. And that's essentially what pointer arithmetic is. And we need to understand that whenever you are dealing with pointers and you're adding values to the pointers, it's actually the size of the target that is being added to it. And pointer arithmetic is used very often in codes that C programmers write. What I mean is, code like this is written all the time. The first one is extremely cryptic. Because it's cryptic, the G++ compiler actually complains at it. That single line at line 4 is actually str copy. That's a string copy. So what does it do? It says, so the steps that is happening for that while loop is as such. First, it says, put the target of source into the target of destination. So assuming that destination and source are pointing to C strings, what it does, it puts the target of source, which is the first element of source, into the first element of the destination, right? After doing so, the assignment operator returns the value that it was copied, right? If that value is non-zero, it means it's not the end of the thing yet for us. Now plus plus has happened, because plus plus as after, it adds it later. But plus plus has priority to target of. Therefore, it's not going to add to the target it's going to add to the destination and the source. Therefore, the address will advance once. Then it goes back to the loop. It says target of source to target of destination. Now we advanced once. What happened? The first character is copied. Now the second one. If what was copied was not 0, it continues. If it hits to the end, now source is 0. It copies 0 to the destination, and 0 is returned. The loop ends. The addresses will still be added by 1, but who cares? It's local variable. It comes out. Therefore, that's string copy. If you do that in G++, it gives you warning. Because it says, hey, in a condition you are putting 1 assignment. It's supposed to be 2 of them. So no matter what you do, it gives you a warning. But it's a perfectly valid thing to do. And they do it all the time. Or string length. I want to find the length of the string. What do? I'm going to pass the string, so S is pointing to the string. And I'm going to keep adding to the address until I hit the null. While doing that, I'm going to add to the variable length. Therefore, the length of the string. We good? So stuff like this happens all the time. In this day and age, people don't like it. They say it's not a maintainable code. It's cryptic. Why don't you just write a loop so everybody can understand? My time, it used to be, because the programs were not as complicated as what they are now. People used to show off by writing codes like that. I'm going to write your function in 1 line. So now if you do that, they fire you. Because so you're writing a code that only you're going to be able to debug, if you can, because after 2 days you forget what you have done. You have to sit over and say, what the heck did I do? Okay? So it's better not to write cryptic code like this and actually write a code that explains exactly what happens. But sometimes to make things faster, you need to write stuff like this. Are we okay? Down to this point? So that's pointer arithmetic in use. Problem with pointers. Okay? So why 2 constants? What does it mean?
One is for the character pointer and one is for the string.
Yeah, what is for the character pointer? The other one is for the target. It means, so in the other one, you saw that I passed 2 constant character pointers, but I modified the pointer, right? Now in here, I'm saying the string is constant, where it points to is constant too, both. Okay? Now it's constant. I want to do some modifications and do something in here. So what do? I do a dynamic thing over here. So I can copy everything and I can manipulate it and find something out of it, for example. Okay? So what I do in here, I'm going to say character pointer a copy will be equal to, I forget about that. Let's not confuse you. Okay, copy, and then I'm going to say copy is new what? New character strlen of str plus 1. And then do something with copy. Okay? Then in here, I'm going to say if, and then at the end, obviously, because I don't want that copy to be a leak, I'm going to say delete copy. Correct? Are we okay with this? Now in here, I'm going to say if something went wrong, You understand it's pseudocode, right? Now what I'm going to do in here, I'm going to say throw something went wrong. Right? Exception handling. Correct? Then in here, when I'm actually working with that, I'm going to be a good boy. I'm going to write try foo with name. And in here, I'm going to say catch whatever. Right? Are we okay with this? Sorry, I have to. My apologies. I have to leave it on. Sorry, because actually, let me just put it on vibration. So I have to leave it on because I may get something emergency. I have to answer that, but my apologies on that. Anyways, so what happens right now is this. If everything goes well, life is beautiful. But if actually I throw an exception, it looks like I handled it properly. But that exception is causing memory leak, isn't it? That's bad. So I cannot throw exception over there. If I want to throw exception, I have to put the whole thing in a try and catch when it throws something. So to actually make this thing work, I have to put this thing in try. I cannot throw an exception over there. And do something like this and say catch. Then in here I say delete copy, right? And then I say throw again. Correct? Otherwise, I will have memory leak. Isn't that the ugliest code you've ever seen in your life? To use exception with a pointer, I have to write my own throw in a catch? What the heck is that? That doesn't make sense at all. It's awful. And that's the cause of most memory leaks that you see in C++ today. Because you have to go through all these hoops to be able to actually manage the memory properly. I wish I could have some kind of a pointer that I did not need to delete. That the pointer knew that, hey, I'm not in use anymore. I have to delete my resources. Do we understand this? This doesn't compile. Reason I'm telling you this is I wrote one of these things and somebody sent me a message, told me your code doesn't compile. I tried to. This is, okay. Pointers fail when using exception. And that's why I actually don't like exception handling. Quite frankly, I don't know. For me, it's like going back 50 years in programming. I don't know, 50? How many years we are doing programming? I don't know, 30 years in programming. And go back to the time that people actually had go-to statements in their code. Because that's essentially what an exception is, right? You're saying if something goes wrong, go to that. Abandon everything, abandon logic, and go to a certain place. They called it exception, so you know it's supposed to happen exceptionally, but hey. Anyways. So how do I fix this? This is how we fix it. First, we're going to pause the recording. We know that online people, you can hear me, right? Thank you. Okay. So let's see. let's use our knowledge of C++ to resolve that problem. So what do? I know encapsulation. We are using OOP345. We are using mostly OOP345 knowledge on this, and a tiny bit of OOP345. So I want to have a pointer, but I want the pointer to remember to deallocate itself. I can simply wrap it into a class. So what I can say I have a class. Let's call it UPTR. That's my pointer. And this pointer, well, I want it to be the pointer to anything, right? So I'm going to say template, type name, and then I'll put over here type. That's my class. So what do I want to put in here? I want to put MPTR. The first problem is solved right there. When I create this, my pointer will be null. I don't need to worry about setting anything to null because I initialized it, right? That's step one. So now I want to create the pointer. So what do? I'm going to say UPTR, and then I'm going to say type pointer, and I'll put the pointer thingy, and I'm going to say by default set it to null, which I don't need to, but anyway. And then I'm going to say MPTR will be set to PTR. That's my constructor. So I'm constructing the pointer. Problem with this? Right off the bat over here, I'm going to fix the problem with pointers not being deleted. Right there. I'm going to say destructor and in my destructor I'm going to say done. So I can set my pointer to whatever I want and then I can delete it. I don't need to delete it. As soon as the pointer goes out of scope, it deletes itself, right? So all I need to do is to make this thing work. So say I have something like this. It's a pointer, right? I say create a pointer, new int. Okay, so let's do it like this. Right? Same thing, right? So I create. Now, just doing this makes my life, like, just take a look at this. I'm just going to run this. How do I run it? There we go. So I create a pointer. There you go, dynamically created. As soon as the program is finished, it's deleted. Done. I created the pointer, and I don't need to delete it. Now, the only problem that remains over here is that I need to be able to do this. I need to be able to say something like that, right? And I want to be able to say cin to target of PTR. I want to do that. But I can't. Because it's an object, it's not a pointer. I use my OOP345 knowledge, and I will say, give me the reference of a type. If anybody accesses this thing using the unary operator, target of, and return target of MPTR. Done. Right? So if anybody uses the unary operator asterisk thingy, it's going to return the reference of what MPTR is pointing to. and problem is solved. Now I can say and I don't need to delete the damn thing anymore. I run the program, it shows the thing, I'm going to enter the value, so let me show. What happened? What did I do? There you go. 1, 2, 3, and it says you entered 1, 2, 3. And walking through it shows that when I come over here, I dynamically allocate the memory for it. And after the memory is dynamically allocated, it comes over here. It actually goes to the operator plus and returns the reference of MPTR. And therefore, that's the one that is going to get received. So when I say 1, 2, 3, and I hit for it, PTR over here is, if I show you, you will see that. Oh, why did I say this? I should, here, it's 1, 2, 3. And it's going to show the value, no problem with that. And when it goes out, it deletes it. Okay? So now if I throw an exception somewhere, I have no problem. When the pointer is dead, I'm done. Everything's good, right? And remember, this could be new int 50. And I have an array of 50 things. It's a pointer. It doesn't make any difference. 1 or 50, same thing. We're good down to this point. Next would be what if I have something like this? Oh. Then if I actually created a pointer like this, I need to be able to say right? I need to be able to say that C pointer of mine and use the arrow, right? Because it's a pointer of a structure, correct? And to do that, again, all I need to do, I'm supposed to receive an address, right? So I'm going to say, what do I say? I'm going to say T pointer this time. So it's going to be operator, like that, and return there you go, problem solved. So it looks more like a, what should we call it? A pointer now. So let me I want to bring the one that is fully implemented. This is not fully implemented, is it? No, we can do more, but let me bring the one that I have fully implemented so I can show you. What I'm saying is that no matter what we do, we know that pointer oh, give me a second. So where did I put it? I guess I did not put it over. Let me bring it from somewhere else. Give me a second. My apologies for the delay. Nah, this is good enough. I'll bring the other one and you'll see. Okay, so now, as you see, I am designing this pointer in a way that no two pointers can point to the same location. I want to enforce that if somebody is using this pointer and setting this pointer to another pointer, two of them won't be able to point at the same location. Because if the two of them are pointing at the same location, when they both when they both go out of scope, the first one will delete. When the second one wants to delete, it crashes, right? So I'm going to make sure that this pointer points to a place in a unique way. So I create a move constructor. First of all, I'm going to make sure that they're not going to get copied. So I deny the copying. And I move the pointer for construction and assignment. Therefore, if one is pointed to another, there is no problem with it. So I can simply, as you see, move one to another, and the first one will lose its data and give it to the next one. Like this, I can simply pass pointers, unique pointers around as arguments, and with the pointer, the data will move to the next one, and it keeps going. And when the pointer is dying, the value will be gone, therefore no memory leak. Obviously, this is not a good thing because sometimes you want to point to the same location with 5 different pointers. We're going to come to that too. This is called a unique pointer, and it is actually implemented. So in here, I'm going to call it my unique pointer. And show you that we actually have this implemented in C++, and we call that a unique pointer. So I include memory, I call it unique pointer, and you see, it's exactly what I have done. The only difference is I have UPTR, you have to write unique underline PTR. It's the exact same source code that I have written, and it's using with that. As again, I told you, things in C++ are not necessarily something complicated. They are simple things that are done with people who find easy solutions for stuff. Now, this is for a unique pointer. Life is beautiful. But it actually becomes shared. It becomes a little more critical. With shared pointers, so this is, I'm going to call it Now let's see how shared pointers are actually implemented. Now get ready for this. I'm going to go through it step by step. Deep breath. Okay? It's going to become extremely boring if I started actually writing the code over here. So I create a class employee because I wanted something complicated to be shared here or there. So that's that. And I overload so the employee thingy has some values over here, and the destructor and constructor is overloaded to get printed on cout. Very simple thing. Now, SPTR is what I call a shared pointer. Now, what is the difference between a shared pointer and a unique pointer? This scenario cannot happen with unique pointers. right? Unique pointer says if you assign the second one, if you do this, as soon as you assign the second one, the first one will go. You cannot point to the same place at the same time. It switches between the two. With shared pointer, that's that way. So how can I track and see that actually several things are pointing, several pointers are pointing to the same location? I can create a counter, right? How did I create a counter? That I could count the instances of an object? Static. We can't. We can. Not for this case we can't. Why? Because static ties itself to a class. What I need to have is a flag for the memory that I allocate. That's the one that needs to be counted. I need to see, I can have the exact, so let's say this big thing over here is an integer. And these are smart pointers to integers. I can create more smart pointers of type int, not like that, more smart pointers of type integer that are pointing to another integer somewhere. So now I have 4 objects of the same type that is a smart integer pointer. And they are pointing to 2 different integers. They are both valid. What I need to track is that when all the pointers pointing to the first one are gone, the target is deleted. Not when one of them is deleted. So for each one of them, I have to have a separate counter created. So I need to have a counter created for this dynamically, and a counter created for this dynamically. And I need to have to point to those. Man, it's going to get tough. Separately, which means it's like that. If I put the static variable inside, all 4 objects would have shared the same counter. But now I can create a separate one as soon as I see a smart pointer is getting created. To point to a memory location for the first time, I allocate a counter for it too. And I keep counting the number of objects that are being created. When they are getting destroyed, I'm going to start reducing the counter. And when everything is gone, I'll delete them both. How do I do that? First, I create the 2. So these are the 2. This is the type pointer, whatever pointer that I'm pointing to. The other one is a size t that counts specifically how many of these I'm pointing, how many objects are created for the one that I'm pointing to. Then, for deallocating, I'm going to create a private function. I call it wipeout. So what wipeout does is this. First, when I actually want to wipe out I want to delete the data, I'll call the wipeout. I don't call the delete. My wipeout says, does my pointer counter exist? If it does, reduce it by 1. Then, if my pointer counter exists and it is 0, actually delete everything. Otherwise, don't do anything. If the pointer is 1, if the counter is 1, 2, 3, it means there is something still there. Still, I have objects there. So wipeout not only wipes out, not only counts, but only deletes when this is the last one. So what do? When I actually create the pointer, smart pointer, and this is a shared pointer now, I initialize the pointer to the address that is coming in. Then I'm going to say, create a new size t. And if the pointer that I'm actually receiving is not null, put 1 in it. If it's null, I don't have anything. Put 0 in it. Are we good? So now I am creating this thing over here. And I'm saying when I'm actually pointing to something, if it is pointing to something, put 1 in it. If they just created a null one, don't put anything in it. Put 0 in it. It means I don't have anything. Are we good down to this point? All right. Now the constructor. First, so that's the constructor. Now what happens if I copy this to another one? What I will do over here is that I'm going to make it point to the other one. I'm not going to initialize a new one. And this one point to the other one too. Then check. If what I'm pointing to is not null, I add 1 to the counter. So anytime a copy is happening, if something is being pointed to, I add to the counter. Same thing for assignment. For the assignment, first, I'm going to wipe everything out on what I have now. So first, it reduces the thing that I'm pointing to now. Then after that, so if this is the last one that is being overwritten, it deletes everything. If not, it just reduces the counter by 1. Then what I will do, I will point to the address of the one that is being pointed to, and then if it's not null, I'll add to 1. So the assignment will do the same thing. The difference is that it wipes out first. For moving, it's a simple move, so there's no problem with it. If I'm copying and I'm move copying, I simply assume everything from the other one. I don't need to do anything. Because it's a brand new object, I don't need to do anything. For move assignment, it's the same. I share the underlying pointer, but I will make sure that I'll wipe out everything. And like this, what I can do is actually see how many things I'm pointing to right now. And do the same overload. Actually, I forgot to do this one. I should have actually extracted the address too. So this one actually does a type conversion. If I want the raw address of the pointer to come out, I can actually use that one. And in a destructor, I don't delete, I wipe out. So wipe out, again, checks if it's the last one, it deletes it. And it works like that. So as you see, I can actually share information between 2 different things. I can have several pointers created to the same location, and don't worry about anything. It's going to delete the target only when all the shared pointers pointing to it are gone. That is a safe. So it's more complicated. Walk through it. But the concept is this. It's going to not delete the target until it is sure nothing is pointing to it. That's a shared one. And the other one is a unique pointer. And this, ladies and gents, so this is going to be my shared pointer. And we have the exact same thing in C++. And I don't know what is this array doing in here, but it is arrow, but anyways. Again, it is in memory, and it's called shared PTR. These are called smart pointers. So from now on, don't use a regular pointer. If you have a pointer and you want the 5 pointers to point to the same location, use a shared pointer. And don't worry about it being deleted. Literally use it as if you are using a pointer. No difference. Just Seriously, I mean, like when you're using it, use it as if you're using a pointer. Just make it a shared pointer if you want 5 pointers to point to the same location, or if you want to uniquely point to it, use a unique pointer. Your choice. Like this, you're not going to have memory leak. Throw exceptions, do whatever you want to do. When the program is finished, it's going to wipe it out when needed. Easy breezy. We good? That's it. That's smart pointers. Done. Questions? That's your next quiz. Quiz number 3, smart pointers. Okay? So I don't know what I'm going to do. Probably I'm going to give you, so next week you have file. Week after, you're going to have smart pointers. Smart pointers, I'm going to probably give you some program with regular pointer. I'm going to say convert it to shared, now compare it to unique. Okay? Something like that. So, so this is, why I keep putting F over is CPP might. That's G, H, CPP. Let me just have a quick look of on what we are dealing with now. I think I need to go to SYL for this. Yeah, we're done. Whoa, next week we have multi-threading, okay? That's the fun part, okay? So smart pointers are done. Well, it's going to be next week, not this week. Next week's going to be a smart pointer. The week after, we're going to have a quiz on multi-threading, and that's the last one. Okay, it's going to be a total of 4, right? Any questions? Yes? File for final? Of course you will. Of course. Oh, yeah. You know what I'm going to do for final? For final, I'm going to give you a file with billion records in it, and I'm going to tell you, write a multi-thread program that reads the file in 10 chunks to the number of processors that you have on your hard drive. So your computer, first you're going to see how many cores your computer have. Then you're going to create a multi-thread program to the number of cores, split the file to that numbers, because you know how to find the size of the file, and then have 10 programs at the same time, read 10 chunks of the file, search for something, and tell you if it's in a file or not. That's your question for final. Yeah, yeah. No, I'll give you the question anyway, with that agreement thingy that I give you for final. Huh? Yeah, a week before, yeah. A week, so. But yeah, I don't know. I just came up with it. I don't know. I don't know if that's going to be the question, but I just gave you an example. It's very easy. With multi-threading, it's very easy to write a question for it. All you need to do is to make the data big and ask you to do it in several processes. That's all. And we are not doing the tough one. We are doing an easy one. Remember that I just to put you in ease. Remember that I told you that there was this commercial for Apple that they would say, you want to do something, there is an app for it. Like, you want to do accounting? There's an app for it. You want to draw something? There is an app for it. You want to do multiprocessing? There is a standard template library for it. So you can, the search that you do, you can simply tell it to do it in parallel. And it will do it in parallel for you. You don't need to code. Of course, I'm not going to do that in final. In final, that's going to be the second question. The first time I'm going to tell you, do it manually. Now do it with standard template. So that's the question for final. Okay, and I'm going to tell you to write it as a template. It's all, you'll have the knowledge. Don't say, It's all the same. It doesn't make it. If you can write a class, write a template for it. Okay? All right. Question?
Professor,
Yes.
am I audible?
What?
Hello. Am I audible? Am I audible?
Yes, you are, very much.
I just wanted to ask that did you set the due date for assignment 3? I was just checking it and I couldn't find any due date.
Thank you. I completely forgot. Can somebody send me a message to set up the configuration for assignment 3? Okay.
Sure.
Okay. Thank you. Just send me a message or Teams so when I go home I don't forget.
On Teams, right?
Thank you. Anyone else? Any questions? Suggestions?
Professor, are we going to have a second quiz next week?
Yeah. Next week is going to. So every lab that you're coming, you're going to have the next quiz. Let's put it that way. Until we get to quiz 4. All right? Thank you.
Professor, are you going to send like a question for the quiz or is it going to be walkthroughs?
No, they're all coding. We don't have any concept. Concept, you do it in final. Concept questions only in final. They're all coding. Okay? All right. Are we good?
Professor, you'll be sending the question, right?
For the quiz, it's already sent.
It's already there?
Yeah, go to the general. Okay, people, you need to sorry. You know what's going to be funny if I go there and it's not there? Give me a second. Of course, it's going to set things up for me now. Thank you. Oh, there you go. Quiz 2 content. Let me fix that. Oh. All right. Content. All right. Have a good one, everyone. Oh, I have 5 messages already. Ooh,